Have you ever found yourself puzzled by a function in TensorFlow, especially when you're coming from a PyTorch background? It can be quite the challenge, right? Well, today, we're diving into the mysterious world of the tf.space-to-depth function and how it works. I totally get it. Transitioning from PyTorch to TensorFlow can feel like learning a new language. You're not alone in this struggle. Many developers face similar hurdles when trying to understand TensorFlow's unique functions. Let's look at the specific question at hand. One user asked, how does the tf.space-to-depth function work in TensorFlow? They provided an example where an input of shape, none 38, 38, 64, is transformed to none 19, 19, 256. If this sounds familiar, stick around as we break it down. So what exactly does tf.space-to-depth do? This function rearranges the data in a tensor by moving spatial dimensions into the depth dimension. It essentially allows you to downsample your input while increasing the depth, which can be useful in various neural network architectures. And don't go anywhere. By the end of this video, you'll not only understand how tf.space-to-depth works, but you'll also see how to replicate this functionality in PyTorch. To understand how the function tf.space-to-depth works, let's first break down its purpose. This function rearranges the data in a tensor by moving spatial data into the depth dimension. In this case, the user has a tensor with the shape of none 38, 38, 64. Next, the user needs to specify a block size. In the example provided, the block size is 2. This means that the function will take 2 by 2 blocks of the input tensor and rearrange them into the depth dimension. Now, let's illustrate this with a NumPy example. The user can create a 4D NumPy array that mimics the input tensor and then manually perform the space-to-depth operation. This will help visualize how the data is transformed. After performing the space-to-depth operation, the user will notice that the output tensor has a new shape of none, 19, 19, 256. This is because each 2 by 2 block from the input tensor contributes to the depth dimension, effectively increasing it. Finally, to create a similar layer in PyTorch, the user can use the PyTorch function called torch.nn.functional.unfold or implement a custom function that mimics the behavior of tf.space-to-depth. This will allow them to achieve the same effect in their PyTorch model. After running the code, you should see that the original tensor shape is 1, 2, 2, 1. And after applying tf.space-to-depth, the shape changes to 1, 1, 1, 4. This shows how the spatial dimensions are combined into the depth dimension. Fun fact, the concept of space-to-depth is similar to how we might stack layers of cake. Each layer adds depth, but we also want to make sure the overall structure remains intact. Delicious, right? Now let's look at the answers provided by other users. Now let's replicate this functionality in PyTorch. You can achieve similar results using the unfold method combined with reshaping. This way you can create a custom layer that mimics tf.space-to-depth. And there you have it. You now understand how tf.space-to-depth works and how to create a similar layer in PyTorch. Remember, mastering these concepts takes practice, so keep experimenting. If you found this video helpful, please give it a thumbs up and subscribe for more content like this. And remember, every challenge is an opportunity to learn something new. This user explains that the tf.space-to-depth function divides the input into blocks and concatenates them. In the example provided, the input size of 38 by 38 by 64 is divided into patches of size 2 by 2, resulting in an output size of 19 by 19 by 256. To replicate this in PyTorch, you would divide each channel into block size by block size patches and then concatenate them. This can be done easily using NumPy. That's it for that answer. Let's take a look at another one. This user explains that the function tf.space-to-depth outputs a copy of the input tensor, moving values from the height and width dimensions into the depth dimension. They suggest modifying the code slightly to see consistent results. After running the modified code, the user shows that the tensor values remain unchanged, demonstrating the function's behavior clearly. That's all for that response. Let's see what someone else had to say. An alternative approach suggested by a user involves using the pixel shuffle module in PyTorch. This module can be adapted to mimic TensorFlow's space-to-depth function by implementing a pixel shuffle with a downscale factor. For example, a downscale factor of 0.5 corresponds to a block size of 2 in space-to-depth. The user provides a code snippet for the pixel shuffle down function, which reshapes and permutes the input tensor to achieve the desired output. They also mention that in NumPy, similar operations can be performed using reshape and transpose. Let's take a moment to review another user's answer. An alternative approach to using tf.space-to-depth in TensorFlow is to implement a similar function in PyTorch. This user suggests using the split and stack functions along with permute. First, you split the input based on the width dimension by the block size. Then, reshape each piece to match the output dimensions. Finally, stack the pieces together and permute the dimensions to achieve the desired output. Let's move forward and look at another answer. An alternative solution provided by another user suggests installing the NVIDIA CUDA toolkit. They mention that this worked for them in their setup